did last time, which was our introduction to heat capacity, which was, we had the magic cylinder, and the magic cylinder is made of metal, and then we started talking about building a fire underneath it, or I got a lighter. Okay, so normally if it's made of metal, it'll shed the heat, right? That makes sense. But what I'm going to do sometimes is I'm going to add heat inside of it, and I'm going to like insulate it so it'll stay hot. And if that happens, the way I can relate the heat to the temperature change is with the heat capacity. And notice that I did not specify constant volume or constant pressure. Let's just stop here for a second. That's what I've got to recognize is that heat is inexact. It matters how you do it. And let me go ahead and preview a little bit. We're not discussing entropy yet, but actually the ways that heat will be a little different is whether it's done very efficiently or not. So in other words, building a fire under a metal cylinder is wasteful, as opposed to maybe having an electrical contacts inside of the cylinder where the heat definitely stays inside of it versus a lossy like fire underneath. Anyway, we're getting there. That's just an example. But the paths that we're going to worry about right now are going to be the cylinder with the piston jammed, or the cylinder where the plunger can expand. But better yet, a metal box versus a balloon. That's even better. Okay, so the path dependence again is going to be, do I heat this in a metal box? And remember that this is our multivariable calculus for what's held constant. And so this heats the heat capacity at constant volume. And again, sorry, my analogies are not good. Heating something in a metal box, or I can heat something in a balloon. Exactly the same thing, except that I have this done at constant pressure. And by the way, what I've been holding constant in these multivariable little derivatives, these slopes of lines, remember that's what they are, so you're familiar with this even though there's different letters. It really hasn't mattered so far what I've held constant. Today that changes. Today, if I hold something constant versus something else, it will alter the result. And remember, the reason was because these are not the same numbers. So I have to actually, to get the same temperature change in my balloon, I would have to add more heat because this is a bigger number. And remember, I told you how to mentally walk your way through that. But the big picture is the balloon expands and I lose some of that energy. So what else do we talk about? I think that was just about, we also talked about how at constant volume there's no work. So in which case the change in U is the change in heat. And therefore divide by, remember you can treat the, this is A equals B, so divide by C, you can think of it like that. Remember this is only true at constant volume. Sorry, I'm not writing very well today. And since we have this definition of U via the equal partition theorem, that's one of those things we have to remember, degrees of freedom. So I'm going to just abbreviate that. Therefore, and I'm answering one of your homeworks right now, the CD of something like helium ought to be something like, what would that be? 3/2 R derivative of T with respect to T is just 3/2 R. O2, which has 2 rotations, would be like 5/2 R. And again, that's because it increases its degrees of freedom. So what I've done on the homework is I've given you a molecule where I've hinted that maybe there's more degrees of freedom, and that's going to affect the CV. So anyway, that's an impossibly obvious hint. If you hint and you don't quite remember, or more accurately haven't looked at it yet, I just answered it essentially. I just made it impossibly easy. What else do I want to say? Yeah, I guess that's about it. Now, again, just review, and remember, you don't really need to write this down. I just want you to, we're always building. The first 2 months of this class, we're going to always build, and the last month we go off into different tangents. We basically finished the remote and do a bunch of random things. So until that happens, the first two tests are basically fully connected to each other. Okay, so I had this nice relationship. The OCD's kicking it. I don't like how it's squunched together. But now what I want to do is, so I got this nice little thing for CV, but what about CP? Now clearly it's going to be the change in temperature with respect to something, right? In heat, it has to be heat, but I already know that. I'm thinking that there's, just like I was able to snarkily slip in U, I think that there's something else I can slip in there, but of course it won't be U, because U goes with CV. Okay, so let me actually just erase this. Understand that I'm actually building towards this, but let me just appear to go off on a tangent and start talking about other energy functions. And how about I introduce enthalpy, which is something I'm having trouble spelling, enthalpy. And this is one of the first things you learned when you took freshman. You learned about enthalpy, and then later you learned about delta G. And so now I'm going to actually get under the hood of enthalpy. You remember that you learned enthalpy was if something is endothermic, delta H was what? Right. Think about it. Right, and then of course if it's exothermic, it was negative. So there you go. That's so you know all about enthalpy. That actually knows you don't have a clue what this is. And actually a lot of this class, you're going to see today that a lot of this class is taking things that we lied. We lied about a lot of stuff to simplify things because when you were 18, we didn't think you were ready for it. So today, I'm going to tell you what enthalpy actually is because what you just said, which is correct as far as your knowledge, is not actually fully true. So, world shade of gray. Okay, so, here, how about I just write it out? H, enthalpy, now not the change of H, I'm going to get to that in 2 seconds, is U plus PV. Now, if you recall when watching the videos or just remember, I said that U is the energy a molecule has, but what I'm missing is like a collective energy, the energy that a whole mole of gas has to make the car piston expand, which then is turned to a camshaft, and that's how you turn a wheel, right? So this addition of PV is designed to capture that ability to move a piston, which I don't really think of an energy of a molecule really doing that. That's a little bit, it's too many degrees of separation. There is actually more to it than just that. And one thing to get very used to, I wouldn't put a star by this, but it's one thing to write down the formula for something, but it's much more instructive to understand how it changes, because if nothing's changing, who cares, right? It's thermodynamics is about how mass is converted, not in a nuclear way, but you know how bonds are broken and whatnot. Things change, which has an energetic consequence, which I care about because that's why my lights are on. Okay, so I don't care too much about this. What I really care about is how it changes. And and hopefully you're getting used to this notation right now. It doesn't seem so weird like it did on the first or second day, where I'm not writing a derivative, I'm just writing change, the top half of the derivative. And of course I'm going to write the bottom half, but I want to do some manipulations first. Now I've already defined the change in U, which is the change in, do I want to do heat, and then the change in work. Something I just kind of simply asked to accept, for you to accept as being true. And this next part, this does need to be second nature. This is the product rule. You let one function remain still, and you let the other guy change, and then vice versa, right? You recognize that? No problems with this? Okay, if you have a problem with that, that's bad because you're going to get about half the rest of the questions wrong. So, even if you're like, what the heck is that? That's what it is, all right? It's really easy, but just don't forget it. All right, so I know that I've already defined work as, sorry, you know what? I'm going to have to make a stipulation. I'm going to have to say that I'm following the reversible path, Because remember, work is minus exterior pressure times change in volume. But if I'm following a reversible path, then it's actually interior pressure. Yeah, P, the interior pressure. Remember, I just say P for interior pressure. When I mean exterior pressure, I have to qualify that. Okay, so again, this is a reversible work. And of course, the reason I do that is such that I can eliminate those terms. And now I'm left with this. Okay, so, all right. Ta-da! Yeah, you don't care, do you? All right, now, what was the original point of this, which I erased? We're still on CP. I was trying to get to CP. Right, now remember, under constant volume conditions, internal energy instantly becomes heat, and I can insert that in heat capacity. It has to be the constant volume one. So I was looking for a nice something similar to that for heat capacity constant pressure. I defined this, which again is a little bit more complicated. You know, this one fortunately you are familiar with, but it's a little bit more complicated than you realize. And I've gotten heat back out of it, but I've got this extra term. I can't just ignore that, right? This needs to be heat. If I'm going to insert this into heat capacity, it needs to be heat. Right now it's not because it's got this extra term. You can't just pretend that it's not there. How can I actually get rid of it? Okay, now what am I trying to do? Heat capacity at? Okay, now help me get rid of this. How can I get rid of that? I want it to be not there. Wait, what was up there?
Like the change in pressure would be 0?
Oh, it's at constant pressure, right. At constant pressure, this is 0. Okay, remember, I had to make a stipulation for CV that I was at constant volume, and then I was able to insert the change in U. In this case, if I am at constant pressure, again, if I had to make a stipulation in the previous example, then there's no reason I wouldn't have to make one now. So to be at constant pressure, there's my stipulation, and sure enough, my change in enthalpy ends up being heat, and I can insert that into my standard relationship for heat capacity, but it's narrowed down a little bit because there has to be a path, the path being that of constant pressure, which again is the heating of a balloon. Yeah, so there you go. There isn't really much else I can say, except that, again, you know that changes of heat are possible. Well, okay, again, let's revisit this idea that enthalpy if positive is heat absorbing, if enthalpy is negative, it's heat releasing. That's what you were taught. But notice that, again, you were taught that enthalpy is the heat exchange, which is this term. And formally, there's that there as well. And that looks up that description, right? But it returns back to what you said, only at conditions of constant pressure. By the way, I'm about to answer one of your homework questions, actually, I think number 1. But anyway, okay, so notice what we've done here. When you took freshman chemistry and we told you that it was heat, did we tell you that it was at constant pressure? Yeah? But seriously, they did? No. Yeah. All right, for the most part, no. You were in an advanced class. Okay, so when you were told that enthalpy is the heat transaction from a chemical reaction, most of you were not told was that actually that was only under conditions of constant pressure. If that was not true, that's no longer correct. In fact, it's the internal energy, but they didn't teach you, except maybe you, for the most part, they didn't teach you about internal energy. So they didn't want to make the stipulation of, oh, by the way, if the chemical reaction is in a metal box, forget enthalpy, it's something else you never heard of. They didn't want to say that. But they also didn't want to confuse you. So they simplified it to the point where it was almost incorrect. And remember, a lot of this class is fixing that. So, yeah, that's the big picture. So we're going to cover a lot of things that you've had in the past, and I'm going to tell you that it was correct, but only under certain conditions. All right, let me go ahead and preview. What makes something spontaneous? Delta G is? Yeah, and here's what I can tell you, maybe. That might be true. It depends on the conditions. Now, here's another thing. So why did we pick H? Why did we tell you H was important for heat and not U? If it was, okay, constant pressure, constant volume. Why did we just decide to stick with the constant pressure? And this is a homework question, by the way. Let me go ahead and answer it. Anyway, let me go ahead and answer it. Actually, let me ask you this. The tree goes under conditions of constant. This is the homework question, right? Number one? Or am I thinking of the, no, this is on your homework. A tree goes under pressure, okay, most chemical reactions, a tree grows, whatever, occur under conditions of constant pressure, right. The world is a world of constant pressure. Now, the way that the tree would grow under conditions of constant volume is I would have to look up and see a giant metal what? Box. A giant metal box. The Earth, no, seriously, the Earth would have to be in a giant metal box, and if that was true, you would have never been told that enthalpy was heat exchange. You would have been told internal energy, but it requires the Earth to be enclosed in a giant metal box. Right, so that's why we told you that. Almost all processes that you will ever deal with are actually under constant pressure. As chemists, we sometimes will do chemical reactions at constant volume. And that is insanely dangerous. We almost never will do this because of the danger involved. What we actually have when the occasions that we do this for whatever reason, I've seen either hunks of Teflon if the chemicals are reactive, a hunk of Teflon that's about the size of a baton, and you use a machine to screw them together. Other times, if the material of the vessel is not so important, again under constant volume, I've actually seen stainless steel used. And that's because if a chemical reaction produces gas, which is kind of common, and it's in an enclosed vessel, it's probably going to explode. And glass, crappy glass that we actually kind of normally work with, that will break at about 2 atmospheres, and that's not very much. 2 atmospheres, God forbid higher, 2 atmospheres is not hard to get to. You've got a chemical reaction producing a moderate amount of gas, and guess what? We tend to heat things. Hits 2 atmospheres, now you're in danger of an explosion, and nothing's worse than flying glass for your eyeballs, right? So we tend not to do that, and God knows everything else in the world is done at constant pressure. Now, in the homework, I had you thinking about, actually, I think it's a protein interacting with a drug, I think, in your homework, and that's going to occur in solution. And now that one's a hard one, because I know what you're already thinking. You're thinking the same thing I'm thinking. Well, this interaction occurs in a little cage of solvent molecules, so that's a constant volume. But now, hopefully, you're also thinking that cage of solvent molecules is not like a rigid piece of metal, like I described in the case of a reaction done at constant volume. It's not a rigid piece of Teflon or, God forbid, metal. Those water molecules can, protein interacts with a drug like on your homework. Yeah, it's kind of in a cage, at the same time kind of not, because that cage can, it's water molecules. You can push them out of the way, and that's right. The answer is that constant volume, constant pressure, the way to figure this out, again, I ask you about a process and I say, is it at constant pressure, constant volume? The hard example is proteins interacting in solution. It's really kind of hard to figure it out. The way to answer the question is, if a gas is created in the process of this whatever, what would happen? Now you can figure it out, right? So in solution, imagine a chemical process occurs in solution and it generates gas. Now it's in a beaker, the gas just comes out, flies off, what, constant volume, constant pressure? Pressure. That'd be constant pressure, that'd be correct. Again, the way to have thought about it is a gas was evolved, the gas would have bubbled out and just flown away. That would be constant pressure. And of course, if the solution, this interaction of proteins generated a gas and it bubbled out, but it was in an enclosed vessel, then it would have been under conditions of constant volume. It would have affected the gas generated. That's how you think of the answer that I did ask, by the way. Okay, anyway, bubble. I'm really rambling here. That's why I want to spill the lecture over to the next one. So here's a whole other way to think about enthalpy, and this is kind of a neat thing you can tell your parents when they ask what you did this week. We're going to cover Legendre Transforms. So enthalpy is actually something called a Legendre Transform. And the best thing about a Legendre Transform is that it kind of sounds cool. You can go around and talk about Legendre Transforms. Right? Okay, whatever. Anyway, that's why I'm alone. So how does a Legendre Transform work? Let me do this mathematically with x's and y's and f of x's because you're used to that. And then I'm going to input u's and h's and v's and p's. Okay, so now also recall that in the first week I said you're going to see this to an unbelievable extent, how a function changes. And of course we're in multivariable calculus land. So f will be a function of x and y, and our little multivariable result for how this function changes is done this way. Remember, it's just a nudge to the right, and then a nudge up and down. Nudge left, right, up and down, there you go. Hopefully you're okay with this at this point. What I need to do is figure out what are the natural variables of f. And so I'll write that down. Natural, help if I can spell. There we go. Natural variables of f. And of course I'll insert them in here. Okay, so this is a concept that only exists in the mathematics of thermodynamics. You will not find this in your calculus book because these are just a bunch of jumbly letters. In thermo, we think of functions. Of course, the function will be u, the function will be h. The functions will be energy functions. Later we'll get to g. So energy functions have natural variables. What are the natural variables of a function? It will be the things that make it change right here. Right here. There we go. So again, I've written something changing. Right now it's f of x and y's and z's. What you do is you look here and here, and now I can see that f is a function of x, and it is a function of y. Okay, it's child's play. Now this, as much as you're like probably cross-eyed thinking, God, this is so stupid, wait till these letters are replaced with h's and p's and v's. It will actually get you a little bit cross-eyed, I'm just warning you. So anyway, again, in thermo class, these functions are energy, they have natural variables, and those are the things that make the function change. So now what I want to do is manipulate that and try to figure out, let's decompose this a little bit more. Now again, I said the function would be like u and h, and the x's and y's would be like p's and v's. Let's look at something like this. Let's look at change in u is minus p dv. Okay, let's go ahead and give an example. Therefore, so f is what? What's f? In this example, f is, come on, this is blinding, yeah, it's u. Okay, and then x is, again, where do you look to make sure that you look to find your natural variable? It's what? V. It's v, right. Here to here, literally it's this childish. Okay, but now the hard one is what is the f? Sorry. Again, I want this to look perfectly because something's wrong with me. What is du dv? It's what? And now again, all right, now there's three parts. You've identified u, you've identified v, and now I'm looking for df dx, so du dv. What's that?
P.
P, you're halfway there. Negative p. Negative p. Right? You see? Changing u is minus p dv. Changing u is minus p dv. There you go. You see how this game works? Now you're going to do it 1,000 more times. So that's not true. Okay. So anyway, now you kind of get the picture, right? I'm still working here. I just want you to get you an idea of where we're going. So we're not worried about this right now. I just want to see you get you to see exactly kind of how I'm going with this. All right. Now this is the side. So we're kind of starting over intellectually. I'm going to write this df again. And df dx, I'll have this on the cheat sheet, but you won't need to have me write this on the cheat sheet by the time we're close to the end of this class, or close to the second test. This will just be ingrained in your head, and if it's not, that's okay, because it's on the cheat sheet. Now, here's my point of this example is, all this stuff means something. So we already saw that this could be P, this could be V. So what I want to do is I want to make, I don't want the calculus stuff to get, you know, a little bit, make it a little bit cross-eyed. So I'm going to call these derivatives, given that they're like pressure and maybe something like entropy. I'm just going to call them C1 and C2 because they're definitely things that I can measure, like pressure and volume. So I want to do that. Okay, now that I have this, what I want to do is introduce a new function, which is the old function minus, and I'm just doing this arbitrarily, C2 times Y. Okay, this is the Legendre transform, by the way. So I'll write that down. Okay, so this is the Legendre transform. This is what it's mathematically defined as. G is a Legendre transform of X. Okay. All right, well that's it. So let's go ahead and move. No, just kidding. All right. Now again, remember I was saying that when I write down functions, I don't really get a heck of a lot out of them. It's when I look at the change in a function, do I start to understand it. I can do this trick with enthalpy and putting it into heat capacity, or I can figure out what the natural variables are. Right now, I'm not getting a lot out of G, so let's figure out what its natural variables are. And to do that, you're going to look at the change in G, and let me manipulate this top of the classroom. And that's going to be the change in F minus the change in C2 Y, which again, we're going to use the product rule. Now I've already defined F as C1 change in X plus C2 change in Y. And the product rule tells me to take C2 and let Y change, and then plus Y change in C2, except I've got a minus sign there. Okay, now I'm using elementary school math to see that the change in G is C1 change in X minus Y change in whatever the C2 really is. And therefore, G is a function of what two variables? Remember, when looking for natural variables of the function,
C2.
X and C2. Okay. Again, I'll just toss this up here, especially for all the YouTubers, which is half the class apparently. All right. So, yeah, there you go. What Legendre transforms do is they take a function that has natural variables of X and Y, and it's going to switch one of them out. You can technically switch two of them out, but I'm just doing just one at a time. I can switch two of them out by taking F and subtracting C2Y and subtracting C1X as well. Now notice another thing, this trips me up sometimes. Look at the Legendre transform equation. Notice that what I did was I didn't subtract C2 change in Y, it's C2Y. Right, that wouldn't make sense to have G is equal to F minus C2 change in Y, because I'd have a function equal to something times a partial, and that's nonsense mathematically. So that's something to look out for. And now that I've defined this, let me show you how H is a Legendre transform of U. And what I've done is recognizing that U, you've already told me, U has natural variables of what? We've actually only done one of them. There's two, but anyway, we've done one of them, and it's what? It was what? V. It was V, right? It's right up there. Okay, so I'm going to subtract. Right. In this case, look up there. This is the Y. But now I need to multiply it by the C2. The thing that was in front of the dy, what was that? You just said it a minute ago. All right, changing y, here, I'll write it down. If you're getting a little lost, it's okay. Minus PDX, sorry, minus PDB. All right, so I've taken u, I've subtracted out one of its natural variables, and then I also subtract out the thing in front, which is what? Minus p. Which is u plus pv. That minus p actually really is a little bit of a biz knocker. It actually, everything with PD will work the opposite of all the other stuff we ever do, because work is defined as minus exterior pressure change in volume. That minus sign actually will always cause problems, a minus sign in everything we do. Anyway, just spoilers. So there you go. So this is enthalpy. Enthalpy is a Legendre transform of U, such that it basically is U, but it doesn't have the volume dependence of U. It has the what dependence? It has the pressure dependence, right? We just went over that. And in case that's not clear, let me just do this another way. I've already done it once, but I can actually do it another way. Change in H is change in U plus the change in PV. And now what I can do is say that the change in U is the change in heat plus, well, here I'm just going to write it out. And therefore, H is a function of P and not V. Now, you may also recall, let me do a little spoiler, don't write this down. I'm not going to write this down because we're not going to get there for another month. Remember what G is? G is H, what? Remember Gibbs energy is enthalpy minus what? TS. We're not doing deltas yet, so H minus TS. G is H minus TS. That sounds familiar? You know what that was? Gibbs free energy. It's also a Legendre transform. G is a Legendre transform of H. Spoilers that it's actually complicated enough that we're not going to get there for another month. So yeah, that's really about all I got. I do want to just use a little bit more terminology, and that is that V is natural variable. I should have told you this already. Minus P is the conjugate. And that's just the thing you multiply by V. You know, since this is thermo class, and all of our functions and Legendre transforms of said functions are going to be energy of some form, U, H, and G. There's another one that we're going to get to in a little bit. They've got their natural variables. I've shown you how to identify that. The thing that they multiply to get energy will be the conjugate of that variable. Okay, in case that's like, wait a minute, what? We've gone over since the first time that pressure times volume is energy. The minus sign is a little IUPAC because of that angle thing, whatever. I don't hate the minus sign, but I can't, no problem. Don't have a choice but to deal with it, right? So, to get energy, which is the only function I care about, from volume, I have to multiply it by pressure, because this is the change in volume, V is the natural variable, and minus P is the conjugate. So just look out for that terminology. Okay, so that is chapter 2, and this brings us to chapter 3, where we're now going to start doing thermodynamic. The title of this section is this traditional, it's called Manipulation of Thermodynamic Variables. What this really is thermo proofs. That's my term because I think it's more accurate, albeit slightly more scary. And so I want to give you 2 examples of the thermo proofs. These are going to be easy examples. But we're going to spend about a month doing this and nothing but this. Thermodynamic proofs showing how things are related to other things. And of course we're going to start easy. And so I'm going to do nothing but examples for the rest of class, and then in the next hour, I'm going to do nothing but work other examples. I hope it seems childishly simple. I guarantee you we're going to get some examples that are not. I'm actually going to begin the next hour with an example that actually is pretty difficult, one of the most difficult And that gives you an idea of what you're heading towards. Okay, so now we're on chapter 3, and I'm going to give it my, I hear you, by the way, I know who you are. So thermo proofs. Okay. Now again, change in F. I told you, you'd be sick of this, but that's not, I'm glad if you get sick of this because that means that you'll ace it on the test. Getting sick of things sometimes isn't such a bad thing unless it's a person. Well, like I wouldn't know anything about that. Anyway, now of course there can be other terms which we'll get to much later in the class. But for now, this is what we've got. We've got our function which has two natural variables, x and y. Now recall that I also did tell you that partials are pointless. They have units, but they have no value. This has no purpose until it's either divided by another partial or it's integrated. Then it has actual measurable meaning. It's either how something changes or it's a certain quantity that can be measured, right? Integrated versus differentiated. So what I want to do is, having written this out, and then of course as we move on, this will be U's, and that will be P's, and that will be V's. But anyway, we're getting there. What I want to do is figure out something that, again, is some kind of measurable. And so I'm going to divide by the change in Z. Sorry, I didn't write this out very well. I need to give myself some room. Now, this again was just some algebra. I've just taken an equation and I've multiplied it by 1 over something. The fact that it happens to be a partial should not really rattle your cage. This is like A is equal to B, and I just divided it by C. That's all I've done. Now, where it gets a little funky is I have to hold something constant. I'm going to decide that later. And notice that I didn't take df dx and divide it by dz. That's mathematical nonsense. For this to have any mathematical meaning, I had to take the x and the y bits and divide those. That's just the one little mathematical topology. I guess that's, I don't know if that's the right word, the one little rule you have to remember. Now also, you do need to set something constant, but I don't need to decide it right now. It depends on the problem I'm asking. I have to find the problem. Okay, so as we've already talked about, let's make FU, let's make XV. This is basically the problem we just did. And because I've asked a certain question, all right, so again, you read out the formula that you're incredibly used to and already sick of, hopefully. We've only really learned about U and a little bit about H, so anyway, let's do U. And I've asked you how U changes with T. So that's why I've said Z equals to T. I can already, so that's the question. And the thing I decided to held constant, I've actually run out of letters, by the way, that's why I'm doing that. I'm actually going to do, I got to remind myself what am I doing? I'm going to hold P constant. Okay, so it's the test. This is the hard derivation question, and I said, what is the change in U with respect to T at constant P? You've written df is the df dx dx, f dy dy. You divided it by dz, and then you identified all the letters, and now you just got to fill it out. Now notice that this part, this is the question. Now the purpose of this df is df dx dx is to simply help you set up the question so that it can be answered. The question remains du dt at constant p. So this part, blah, 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 blah. We're done. Forget it, right? To answer the question and get full credit, you have to do the rest of this. So now we need to start taking these bit by bit and breaking them down, filling them out, and so you get your points, right? So I've already identified, so we've got to identify this, and then I'm not going to worry about this for today. We've got to identify this, and let's do that. So the first one is that I've already identified, let me write it out. The FDX constant y is the u dv, and again, I'm just making substitutions like I was a middle school student. And this is minus p. Right, this part right here, the change in u is minus p dv. Okay, now I hate to bring this up, by the way, but notice that I never defined what y is. I hate to do this because we're not there yet. Y happens to be entropy. You don't even need to write that down. We're not going to do this entropy term because we're not going to be there for about another month. There's nothing to it. There's nothing magical. It's just that I need to go in steps, and I'm going to just start right here. At the same time, I don't like simplifying things to the point they're wrong. Y happens to be entropy, but we're not going to do the Y part. We're going to do the V part. V, entropy, forget entropy, we're doing the V part. Okay, anyway. So I've got this part solved. Now I've got to do dx, dz at constant question mark, which is, again, I'm just filling in what I've written this out because I'm familiar. This is what I actually have to answer. Okay, so now I got to do this. Okay, now I would have also told you in this question on the test, this is a hard question on the test, that you can use the perfect gas law. Now that should be a big hint to put in what for V. What do I do next? And again, I've said you can use the perfect gas law. You have to get this. If you don't, you're only getting half credit because you got this part, you got to get this part, you got half credit. Full credit, you got to do this part. The question said,
RT over P.
yes, RT over P, nRT over P, dP, and this is actually a constant P. Now, this actually won't change anything. I do want you to...
DT over D?
T. Right. Sorry. Right, it's right there. Yeah, thanks for catching that. I do that a lot. Just on automatic. Okay, so again, you're like, what? Well, I told you to use the perfect gas law, so the perfect gas volume. Now, this is unanswerable by itself because I'm asking how this function changed with t, but there's no t in it. Oh, really? Yeah, there is by the perfect gas law. So what's this? Remember, this is a constant times x, and I'm asking the derivative with respect to x. So what is the result?
That's N over P.
nR over P. Sorry, I heard about 20 things at once. nR over P. Remember, a constant times x, the change with respect to x is just a constant. Just recognize that it's a t, and the constant's nR over P. This is childishly simple. So you got to remember that. Oh, now what if I had done the van der Waals? So, an aside, van der Waals. Like on your homework. Oh, by the way, yes, this will be on your test. Something like this will be on your test, not necessarily this. Okay, so I had asked du dt at constant p for the van der Waals equation. Well, let's say I had done that. And, sorry, my bad. I can't really do that. I can't really do this for van der Waals. Let's say I had changed, let's say I was asking this, dp dt. The constant v. And let's say I had done this for the, if I did this for perfect gas, that would have been nR over v, but if I was doing the van der Waals, what I would have, sorry about that, I kind of got a little disconnect there. What I would have, I would have given you the van der Waals equation, and I'm using the, not the VM version, just no reason. I think it's just a little bit easier to look at it this way. Okay, again, we're doing these thermodynamic proofs. For whatever reason, I've asked you to do dp dt, and I've asked you to do it for the van der Waals equation. And based on last time, I don't think I can ask what you think it is. I'll just have to write it out. We need to do clickers, I guess. And there you go. And what's kind of nice is, now I said this before, any result I have with the van der Waals equation or that other equation I've chosen to use this semester, if you eliminate the real gas parts, you ought to return the perfect gas. So B would be 0 for a real gas, and I end up with nR over V, which, right, that's right, that would be dP dt. So, last bit. So that's one way that I'm going to, that's one regime of questions I'm going to ask you to do, either again thermodynamic manipulations. Here's the other manipulation I'm going to give you. And this is the integral form. So I've given you the derivative form. Tell me how u changes with v. I don't know what that other question came from. I think pH with respect to T is constant. Anyway, sorry about that. This is the other way I could do this. I could ask you what is the change in F with respect to X if it's equal to Z. I want to point out to you that therefore the absolute magnitude of the change, and say this is the change of internal energy, would be this. Okay, so again, using this concept of this is like A over B equals C, then A is equal to B times C. That's what I've done. And partials need to either be divided by partials or integrated. This, I did the first one up there. This is the integral form. So let's do this. Let's do dP, dP, and let's say that volume was held constant. And I'm just kind of picking this out of my rear end, by the way, because I can. And what I'm going to do in the next class is show you a little bit how I pick questions, and I think that will be instructive. So I've given you this, and now my question to you is, how does P change with T? And what you do is, again, using just algebra, you do this. Not much to that. Now remember that volume was held, first let me go baby steps. Again, partials must be integrated because in this case I asked you to do that. And so this of course turns into delta P. But let me handle this part. Now, this is kind of important because N and R are by definition constant. I'm not going to change gas molecules. R is by definition a constant. V is held constant because I told you it's held constant right here. Those can come out of the integral. And I screwed up. Look at that. Right? Right, sorry. Catch me if I do that. Okay, and therefore, delta P, and of course this is NR over V delta T. Okay, so again, the second type of question I will ask you is I'm going to give you this, which by the way will be the answer to the previous question. Look for me to do that. You need to, here's a real example. You juggle the partials. Now they're in the integratable form. You recognize that this can come out of the integral, and then you just use some first semester calculus to get the answer. Now this is in contrast, sorry I'm going a little bit over. Let me show you how you screw up. It's great to know how to do it right. It's also great to recognize when you've done it wrong. Here's how you do this wrong. It is true that dP dt is nR over V, but nR over V is actually P over T. That is correct. Okay, now I'm kind of out of time. Let me show you that question. This is very similar to what you had on your homework. So therefore you juggle your variables, you do this, and what you end up with is ln pf over pi. Those are your limits of integration equal to ln tf over ti. Okay, something went horribly wrong, folks. This and this are pretty different. And yet I don't see that I did anything wrong. And let me tell you, nR over V is P over T. That is correct. I can juggle letters around like this. That is correct. The derivative of 1 over P is natural log. Apply limits ln pf over pi. That is correct. But this is not this. That is not correct. I have done all the steps correctly, but come up with two different answers, and that should really bother you, especially because you're going to lose points if you give me this one, right? Anyone resolve? How can you resolve it?
The constant?
Yes, the constant. The volume was held constant here, but was it held constant here? It was not held constant, that's correct. Because it's snarkily hiding inside of here. You see, when I integrate P, when I integrate the 1 over P, this affected the result. And that means that it's changing. The T is changing. You know, the fact that the P is here and the T is here change the results into natural logs, right? You know that, and you just saw me do it. But should they have? No, of course not. They shouldn't have changed the integral at all, because had left them in their original form. It's the number 5, and the number 5 doesn't do anything. It just remains. So fundamentally, it changed the result, but it shouldn't have, because it should have never been part of the integral to begin with, because volume was held constant. Basically, by holding volume constant, P over T cancel each other out. That's the big picture. But when you integrate them, then you unbalance that. And you shouldn't have. You shouldn't have, because the experiment was done in such a way that it did. Anyway, if you fall, if there's any potential for you to fall into this trap on homework, I hope so, because that's how you'll figure it out. If there's a potential for you to do this on a test, I will make sure the question is worded in such a way that you won't. So don't worry about it. So, as usual, I've gone over 10 minutes.